Atomic number has the symbol Z, capital letter Z, and it is the number of protons an element contains. And you can see in the picture here the atomic number is at the bottom of that symbol, the bottom left. The mass number is at the top left. For this case, magnesium has a mass number of 24 and an atomic number of 12. The mass number, which has the symbol capital letter A, is the total number of nucleons in the nucleus of the atom. In this case, a magnesium atom has 24 nucleons, and nucleons are protons or neutrons. And so if magnesium has 12 protons given to us by the atomic number and a mass number of 24, then the number of neutrons in that atom will be equal to A, the mass number, minus Z. So in this case, we have 24 nucleons minus 12 protons, and that's going to be equal to 12 neutrons. This table here is something that you might see on a test question or something like that, where you have to fill in the missing boxes. And so as we look at that, start off, we got potassium, which has an atomic number of 19. That tells us that we're going to have 19 protons. It has 19 electrons in this case, and it says it has 20 neutrons. So the mass number A, which is P plus N, is 20 plus 19, or 39. In the second row, all we're given is the mass number and the number of electrons. Now, when I made this is actually from a different class. I talked to them about how the atoms in their part are all neutral. And I don't think that this chapter has yet talked about ions, so I'll keep it the same where it's neutral. And so that means that there has to be the same number of protons and electrons since they're neutral atoms. So because that's 5, that makes that 5. Since it's element number 5, because there's 5 protons, that means that this is going to be boron. And so we have an atomic number of 5 because there's 5 protons, and now we need the number of neutrons. So the number of neutrons is going to be A minus Z. So we get 11 minus 5, and that's equal to 6. In the third row, we have sulfur. It's got an atomic number of 16. It's a mass number of 32. We could, since we have both of those, we can do 32 minus 16 is equal to 16. Since the atomic number is 16, we've got 16 protons. It's a neutral atom, so it has to have 16 electrons. In the final row, we have vanadium, and it just gives us 28 neutrons. So we have no way to know the mass number or the atomic number or the protons or electrons strictly based upon the number of neutrons. But if you look at a periodic table, you can find vanadium, which is element 23. And so you'd have to look at a periodic table to do this, but luckily I don't ask you to memorize things. So you use your resources, you'll find it in the periodic table at element 23. So that makes both of these columns 23. And for here, the mass number is going to be 23 plus 28, which is 51. Isotopes are multiple different atoms of a particular element that each have a unique or different number of neutrons. Like hydrogen has H1, there's H2, and there's H3. You can see they have different mass numbers, 1, 2, and 3, but they all have the same number of protons, 1. Those are isotopes. This isotope is called protium. That isotope is called deuterium. Pro meaning like the first, DEU for 2, and then H3 is called tritium. Now, atoms of the same element that are isotopes are basically, they have the same chemical and physical properties to within a certain degree. So they don't really change how chemical reactions go. They might slow the reaction, like if you go from hydrogen 1 to hydrogen 3, it might slow a respective reaction down by somewhat less than 1% or something. But ultimately that doesn't really make much of a difference in small quantities. Now, I've read that if you were to take water, H2O, and you replaced both hydrogen atoms with deuterium atoms, which you could also write with the letter D, so you have D2O, that if you drank a sample of water, or what's called deuterated water, or just D2O, if you drank pure D2O, and you did this for a very, very long time frame, like a couple weeks, maybe a month, it would actually throw off your circadian rhythms and potentially could kill you through toxic poisoning. But that's a lot of D2O, which is not going to happen in the normal world, so not something you need to worry about. The table here shows the name of the isotopes, the number of protons, number of electrons, the mass numbers. That's the key thing to look at, and then the number of neutrons. So you can see there's 24, 25, 26. They each have the same number of protons, but the number of neutrons increases by 1, just like the symbol. The thing at the bottom, the percent, that means like the abundance of each isotope. So if you had a strip of magnesium, 78.7% of the atoms would be magnesium 24, 10.13% would be magnesium 25, and 11.17% would be magnesium 26. By observing the proportions in which elements combine to form various compounds, we were able to calculate relative atomic masses. The standard of atomic masses is the carbon-12 atom again. In this system, carbon-12 is assigned a mass of exactly 12 atomic mass units, AMUs, and every other isotope of every other element is based on this, like I said earlier. If you look at the periodic table for the atomic mass of carbon, you'll see that it's 12.011 and ultimately AMUs. How is it possible, based upon the fact that carbon-12 is exactly 12? Well, the reason is that a sample of pure carbon has these different isotopes in there. There's carbon-13, there's carbon-14, there's other ones even. The only ones that are really that important, though, are going to be carbon-12 and carbon-13. Carbon-14 is in samples. It's used to radioactively date dead organic matter. So it does exist, but it is such a tiny percentage of all of the atoms that it's not necessary to use in getting the atomic mass of an element. So thus, the atomic mass reported on the periodic table is actually an average atomic mass of all isotopes of each element. So for carbon, it's not going to say 12 because it's an average of the 13 and the 12. Now, if they had 50% of the atoms being carbon-12 and 50% being carbon-13, then it would be 12.5. Since the actual atomic mass of carbon is 12.011, you can see that most of the carbon atoms are going to be carbon-12.